normal MOSFET. That's why we cannot use MOSFET below 45 nanometer technology. So that is what I will be talking more on these devices, transition from micro to nano. Then we'll have a small comparative analysis between MOSFET and FinFET, and FinFET based few circuitries I'll try to discuss here that I have explored with LT Spice simple simulation tools, and I have explored this FinFET structure at nanoscale till 40 nanometer using TCAD I think almost 5 to 6 years back. So that work also I will try to say here. So to begin with, this nanoscience is a study and application of small, extremely small things used across all the streams of science, maybe it is chemistry, biology, physics, material science and engineering. But what is nanotechnology? It is a way to put the discoveries at nanoscale to work. Okay, nanoscience is a study of extremely small things, you say, but nanotechnology is a way to put the discoveries to work. Okay, this nanotechnology may be able to create many new materials and devices with vast range of application, such as medicine, electronics, biomaterials and energy production. So these are the carbon nanotubes and pictures what I am showing here. So this carbon nanotube is used as in place of channel. So channel we were creating in the MOSFET, that was a silicon made channel only, but here we are trying to replace that channel with the help of carbon nanotube, and even people have explored that with a graphene as well. So how small is this nano? How you visualize it? Okay, so 1 nanometer is billionth of a meter. It is 10 to the power minus 9, right? How small it is? Can you imagine? A sheet of paper is about 100,000 nanometer thick. Human hair is about 50,000 to 180,000 nanometer in dia. Still hard to digest or understand, right? You can consider this way. You assume you have a country population as 100 crores. In 100 crores, one person, identifying one person in a crowd of 100 crores is 1 nano. You try to imagine this way, try to visualize this way. Okay, so that is nano. You will not be able to find a person in that crowd, right? So that is a size nano we are talking, and sir was mentioning Nikhil Rao sir, 1 atom thick transistor. Okay, so angstrom we are talking. Okay, few atoms put together, transistor they have built, already demonstrated. But to come to the market, it takes a lot of research and verification, and then building a product on that, and then releasing to the market. There are many challenges. Okay, so these are some examples. Okay, water molecule of what size? 0.1 nanometer. Glucose 1 nanometer size. Antibody, virus. What is the size of a coronavirus? Yes, around 100 nanometer dia. Okay, it was varying. People have claimed 80 nanometer, 120, 150, different values you will find in the literature. Okay, so that is the size of the virus. Okay, so we have nano devices today developed by many researchers in the field of this nanotechnology and nanoelectronics, nanoforce and nanotubes, quantum dots, nano seeds. Okay, there are plenty. So this is just an example to give how small is nano, and the nanotechnology and the nanomaterial research. Actually, the person who gave a lot of importance and presented many papers, research papers in conference that is Richard Feynman. Dr. Richard Feynman was the physics professor, and he stressed more on this nanotechnology. And 1950 itself, he presented the concept in the one of the conference. He shared his thought process on the technology. So invention of scanning tunneling microscope in 1981 and discovery of fullerenes. Fullerenes are nothing but allotrope of carbon. So we are talking here C60 in 1985 led to the emergence of nanotechnology. Okay, so the term nanotechnology had been coined by Norio Taniguchi 1974. So what he said is, bottom line is, there is a plenty of room at the bottom. Means next big thing is very, very small. That is what he tried to convey to the audience sitting in the conference hall that time, okay, when he was discussing his research. Okay, so this nanotechnology is not new, because you see some of the pictures here. Gold nanoparticles in glass are reflected as red, and you have seen your ancient stained glass makers, they knew very well that if they put finely ground gold or silver particles in the glass, they would get beautiful colors. I think you have seen optical properties change with the nanoscale. So what is making the difference here? The size is making the difference. Size of the material changes, the properties of the material changes, and you are exploring that way. You are trying to utilize the properties that are helping you. Okay, so why? Because these are some of the examples I have collected here. What is the speciality about this nanoscale is short answer. What is the answer? Materials can have different properties, useful properties at nanoscale. That is a beauty. Okay, some examples I have given here. Some are good at electrical conductivity, some have strong magnetic properties, some are stronger, some may change the colors as the size changes. So one example is, see, you have seen soda cans made up of aluminum, right? So aluminum is used to make harmless soda cans, but in a powder form it can explode violently when it is in contact with the air. So that is how the property changes with the size. When it is in the can form, soda can form, okay, you are using it for storing soda, right? Aluminum material you are using. But when it is in the powder form and when it comes in contact with the air, it will explode, right? So property is changing. Carbon atoms bound together in a relatively loose configuration may create coal or graphite. You have a pencil you are using, right? So that graphite is found in pencil, right? Because there the carbon atoms are configured loosely, they are bounded loosely, they are not tightly configured, they are loosely configured. So in tighter configuration, carbon makes diamonds. That is a beauty, right? So precise configuration can create carbon nanotubes. The strongest material estimated to be 100 times stronger than the steel. Different literature, again there is a difference, but it is very strong at nanoscale. Okay, that's why we see a lot of CNT, carbon nanotubes, used in bicycle parts, car parts, and lighter materials parts in the aeroplanes when combined with plastic. So used in water filtering, you have a membrane in water filter and that is coated with carbon nanotubes today. Okay, so filtering, water filtering also it is used. Membrane you have seen, right? So sensor to identify contaminants in water systems. Used in flat panel displays of color TVs. Okay, and it is used in batteries as well. So these are the few applications just I have put here just to motivate you to take up the job in this area. So carbon nanotubes have plenty of application in sensor design, in water filtering I told, coating the material when it is mixed with plastic, it will have strength, and no, it is used in aeroplanes parts, medicine. Today people are able to build a sensor that is able to kill the cancer cells in the human body. Okay, so this people have proved already. Okay, a lot of research is taking place in this domain, nanorobots, and even this carbon nanotubes are coated on the or used in developing solar cells. So you take chemistry or environment, consumer goods, military and security application, you have plenty of application for this nanotechnology, nanomaterials, and so this is the impact of nanotechnology on the economy of the country. If you want to just see some literature, you will find plenty. Okay, today we need 5 million workers worldwide in the field of nanoscience and nanotechnology. In addition to that, you need 7 million workers in support of these areas, so as a support staff. Nanotechnology is expected to reach $8 trillion industry by 2024. Nanotechnology is enabling technology that will change the nature of almost every human-made object in the coming year. So we come across fabrication techniques in nano. One is top-down approach and bottom-up approach. And you understand what is bottom-up. You top-down. If you see, start with large material and bringing down it to nanoscale. So you are scaling down the size from bigger one to smaller one. Okay. So as I said, MOSFET we scale from micro to nano. Now we are exploring at nanoscale till many fab units are producing the chips with a size 180 nanometer, most of the foundries, but researchers and few foundries, if you take Taiwan, TSMC, till 3 nanometer they have explored and they are able to fabricate the chips, and they have demonstrated. But there are plenty of challenges to be addressed. Even FinFET, we are talking, FinFET is a nano transistor today used in chips, high performing computing systems and all. Already it is used. Your memory, SRAM is designed already using FinFET. You have chips available in the market. Okay? Sorry. Right? So all that is, see, scaling we tried in MOSFET, and till 45 nanometer it is working fine, but beyond that we have to go for different device structures, FinFET or carbon nanotube FET or graphene FET or nanowire. Okay, I will show some of the structures. And bottom up it is exactly opposite. Start with individual atoms and then you start building the device or the sensors or whatever system, electronic system you want to build. Okay, so these are some of the application, some of the chips available in maybe camera or maybe in storage device. People have used nanotechnology already. Nano transistor based chips are available. Okay. So these are some examples I have put here. Okay. So nanotechnology in computers. So silicon transistor in our computer may be replaced by transistor based on the carbon nanotubes. So Stanford, if you see Stanford, Berkeley, and then Purdue, lot of professors with research students, lot of work they have done on this area. Okay, carbon nanotube based devices, carbon nanotube based chips they have developed. They have even developed sensors, lot of sensors based on the carbon nanotube. So they are moving from silicon to other devices, materials, just to have these advantages. What I was talking, flexibility, strength-wise, and the current conduction speed wise, the processor speed designed with carbon nanotube will be very high compared to silicon based chips. Okay. Nanorods is upcoming technology in display techniques due to less consumption of electricity and less heat emissions. Researcher at North Carolina State University says that growing arrays of magnetic nanoparticles called nanodots are helping them to build the chips for different applications. So nanotechnology in memory and storage, if you see the progress, 1980 we paid or the cost of the 2 GB storage was $80,000, and 2 GB in 1990 it was $200, and 2 GB in 2010 it is $5. That is how, as you scale down the device size, you improved in bulk production, definitely cost goes down, and the people were able to reduce the cost. Yes. So nanotechnology in memory and storage. Today you can think of having 1000 GB of memory on a head of pin. Okay, the picture is shown here. Head of the pin. You see the area on that. You will be able to store 1000 GBs, 1 terabytes of data. How it is possible? Can you imagine? Can you just think on this? How it is possible? But we have this technology today. Okay. So I'll come to electronics part. So that is the background for nanotechnology, nano devices, nano materials, what we are discussing. Now how we move from micro to nano. MOSFET, when you start scaling, what are the challenges that you face? There are plenty of issues that many researchers are working on, and a few of them I'll try to highlight here. So Moore's law, as many speakers, the morning speakers, they were also talking. Every 18 to 24 months, the number of transistors on the chip doubles. That is a Moore's law. Moore's law says 18 to 24 months, number of transistors on the chip doubles. Okay. So I think I did not get recent graph. Just 2010. Okay, up to 2010 I have a number of transistors over the period of this time, 2010. What is the number of transistors they had on the chip? Okay, today new processor, if you see 2 to 3 billion transistors you will find on the chip. Okay, even in the memory chip you will find billions of transistors today. SRAM memory I am talking. Okay, so Samsung started working in 2016. They released the product to the market, memory product, SRAM, with FinFET technology in it. Okay, so almost 14 years of effort. You can see. Okay, how they think next 10 years, 15 years, what technology will come to the market. Okay, keeping that in mind, that vision in mind, they start working, and they grab the market. Okay, so silicon transistor computer may be replaced in coming years by transistor based on carbon nanotubes, and because the consumption of power is very less in CNT compared to silicon. So this is a structure, cross-sectional view of this MOSFET I have shown here. So as I said in the beginning, MOSFET ruled our semiconductor industry for almost 4 to 5 decades. Okay, right? So, but when you are talking about nano, of 90 nanometer, 65 nanometer, till it is working fine. But below 45 nanometer, I will also show some results. The behavior of this device changes drastically, and you cannot use it as a switching device anymore in the ICs, because below 45 it will not behave like a normal transistor. So that is I'm sorry. So why we are scaling MOSFET? Because of these. I'm sorry. Sir, one second. Okay, no. Sorry. Yeah. So why we are scaling down MOSFET size? Why we are moving from micro to nano is because everybody wants smart, sleek mobile phones, right? You want all features with the same chip size of the chip. With the same size, you want plenty of application future in it, right? So that's why everybody want attractive smart mobile phones, smart systems, smart watches, right? So size reduction is as per this Moore's law, we keep scaling down the device size to make a compact and less power consuming, faster chips for the application, right? So higher the density, lower the cost. More number of transistors on the chip, and when it is produced in bulk, cost goes on reducing. So reduced power consumption because the size of the device itself is scaled down, so it consumes less power in the switching process, and faster the speed because you have brought source and drain closer to each other. The speed will be faster. The channel length itself is reduced. Okay, that's why. So these are the major challenges that we face when we move from, or when we scale MOSFET, scale down MOSFET. This is one channel length modulation is one issue. Drain induced barrier lowering is another issue. Increase leakage current. Yes, velocity saturation. I will not go in detail. Just I will try to touch upon these issues. So MOSFET scaling will soon reach a dead end with the short channel effects severely affecting the performance of the device in reality. See, what is happening is when you are scaling down the MOSFET size, you have source and drain. When they come closer, you will lose the control. From sitting at the gate, you will not be able to control the current flow through the channel effectively. So that is the main drawback why we have to look for alternative device structures. Okay, one gate you are not able to control the flow of current. That's why you need to go for multiple gates or gate all around structure in order to have better control over the channel. Okay, so yeah. There is a scope of designing accurate and computationally efficient compact transistors, models, and faster memories for future smart system based on digital India and world. So this is a structure, FinFET structure, ARM company, web I have taken. So you can just see, observe. You have a source, you have a drain, and you have gate. Gate is wrapped around the channel actually. Source to drain, there is a path for the current flow channel you have, and that is wrapped by this gate. So gate is not at one side, it is wrapped around the channel. So you have better control. This is the FinFET structure. MOSFET structure, I think in the beginning you observed only one gate. Okay, so when you scale down, it's very difficult to control or have the control over the channel. So now gate all around or multiple gate device is a FinFET, FinFET. MOS FET, metal oxide semiconductor field effector transistor it is. Here fin FET, same FET, but fin is it looks something like fin of the fish. The structure looks something like that. That's why the name fin FET they have given, and that is multiple gate device it is. Okay. So you can just source major 3 terminal device. One is body. We usually don't mention it. Source and drain and gate. Okay. So yeah, you can just see FinFET structure. See, gate is here, both the sides gates are shown. Channel is the path for the current flow between source and drain, but gate is sitting both the sides so that you will have better control over the device. Nothing more than that. So this is one more device you can explore in the research. It is microscopic wire. It looks like a wire. That's why it is nano wire they call. So it is in the order of nanometers. Okay.
Sir, it is always cylindrical.
Yes, sir. Because it looks like a wire. Wire is cylindrical. So size is.
We can have a square kind of a wire.
You can have, sir, but see, when you wrap up the gate around the channel, the finishing and the structure also matters, because leakage current and all. Square may, I think some papers you will get it. Leakage is more, they say, current leakage. So when a gate is wrapped around that like this, with this shape, leakage is less. That is what literature says. So this is discussed more in the research than any other say. So yeah. So here also you will have source and drain, and channel is wrapped all around. Okay, with a gate material. So because of its one-dimensional nanostructure, it can efficiently transport electrical carriers. Right. So I was talking about carbon nanotube based devices. This is a carbon nanotube transistor. Carbon nanotube. See, complete silicon is not replaced by carbon. Only channel is replaced by channel. Earlier was silicon made. So that channel, only channel part is replaced here with the carbon nanotube. You can see this. This is a channel, or this is a path between source and drain. This is built using carbon nanotube, and people have proved that the current flow through this is far faster. The flow of current.
I have one question.
The switching. Yes, sir, please.
What about channel formation when we are using the nanotube as a channel?
Nanotube.
In case of the normal MOSFET.
Yes, sir.
The operation is such that there is a formation of the channel of electron when a voltage is applied at the gate.
Yes, sir. Yes, sir.
So how the operation is different in case if we replace the channel by the carbon nanotube?
Sir, actually this is when they replace silicon with carbon nanotube. The conduction of charge carriers is very fast. The current conduction will fast. Switching speed of the device will improve. That is a research literature says, and I have explored with a tool. I will show the result next. So that also shows on by off current when I have measured with the TCAD tool few years back. This is giving better performance and less leakage current compared to this. But when I ask industry people, foundry people, they say there are plenty of challenges when you interface different material, carbon nanotube with silicon. So fabrication challenges are more, they say, but with the tool, TCAD tool, I am able to get small improvement in the ion by IF ratio and leakage reduction.
Earlier you said that there is a channel width modulation. So that channel, how by using the carbon nanotube as a channel?
Sir, working principle almost remains. Only material you are changing just to increase the speed of the device. Okay, so because material property as nano size, this carbon nanotube is giving better electrical conductivity. So that only conductivity part at the channel will improve, but there are challenges when you go for the fabrication. That's why it is not there in the market today. But at research level, research labs, Stanford and Berkeley, few professors, even Purdue May, Supriyo Datta, they have explored some devices, sensors using this carbon nanotube with because of its sensitivity. They have explored, they have built the sensors. So small research work is available to demonstrate, but it is not in practice. It is not, no device or the chip is available with carbon nanotube based material in it. So maybe challenges, as we are discussing, challenges are there, but there is a scope for improvement, and if people can try fabricating this with the same this one, definitely it will. But fabrication difficulties, they say only conductivity parts it improves. Rest there are interfacing issues will be there, because when we are interfacing silicon with other material, definitely that challenge. And oh sorry. So 5 minutes, we'll break for tea. So this is a geometry of the device in FinFET. So what is the gate length, what is the fin height, and size of the oxide layer, because SiO2, MOS metal oxide layer is insulator, right? So what is the size of that, what material you can explore to improve the leakage or reduce the leakage in the device, and that helps you in reducing the power consumption of the chip. That is the ultimate goal. And this is a platform simulation setup I did, and I worked on FinFET to some extent with the TCAL, global TCAD tool in 13-14.
Is it freely available or it's a licensed version?
Sir, it was a student version available that period.
It is available.
Now it is not available. I tried to purchase with management support, but the cost was 8 lakhs that time. Now they have reduced it to, I think, 5 lakhs.
Per year?
Yeah, one license per year, it is costing 5 lakhs. Today also, sir. Because some students interested, I wanted to tune and give small work, but I am not able to do that because of the cost. Because no college will be interested in purchasing this just for the sake of research. So that is how. But we could develop the mesh, the structure, FinFET structure, and simulate in TCAD, and now I have recorded the result. And this is a FinFET for 22 nanometer and 14 nanometer. Both the characteristics curves I have obtained here. At 14 nanometer, this is a curve, and 22 nanometer size, this is a current curve with respect to gate source voltage. Okay, so the magnitude of the current you can see at 0 itself, you have a current magnitude this much at 14. So FinFET works fine at nano. MOSFET, it will fit. Maybe 1 or 2 slides if I have, I will show you. So that's what ion by I off. On state current to off state current. The ratio is very large at lower node size. So, but it can so happen that at 0 volts itself, your device may turn on. Imagine. So some challenges with FinFET also you will find, okay, when you are doing the research. So transconductance is a ratio of drain current to gate source voltage. That ratio at a different node technology, 32 and 22 nanometer, even 14 nanometer, I have explored, and transconductance improves with reduction in the node technology. but these two graphs are showing the transconductance for FinFET as well as nanowire. So nanowire is also compared because both are nano devices. I cannot compare FinFET device characteristics or transconductance parameter here with MOSFET because I am not able to explore MOSFET at 22 or 14 nanometer. Because below 45 nanometer MOSFET fails badly. It won't be able to give the result expected. Okay, so what I have tried in my research is I tried replacing the SiO2 silicon dioxide material, the oxide layer, by high K dielectric material, maybe titanium oxide, and few more I will show you. Yeah, these are the materials. Yes, no problem. So this is a gate material. One is device structure, FinFET structure I explored, and then I replaced SiO2 material, that is oxide material, by titanium oxide, and zirconium oxide. These three materials, I recorded the result, and ion by IF ratio is improving. With titanium oxide, I was able to get better ratio, higher ratio, means IF is leakage current actually. It is less the leakage current, the ratio is, yeah. So leakage was reduced here to the expected level. So this was the better result in my all three possible combination of materials. Can I suggest
something in this?
Yes, please.
How do you have a different ion and IF current separately to know exactly how much amount of leakage current is there in each case? Okay. Instead of taking the ratio.
Yeah. Okay.
Because there is a possibility of conduction or switching on during the off state also.
Okay, got it, sir. Got your point. Good, sir. Thank you.
There is a possibility.
Yes. So, actually, your leakage mainly depends on the oxide layer. So, but SiO2 you cannot further scale down. You cannot scale down to 3 to 4 nanometer size. So that is a challenge when you scale down MOSFET to nano. So that's why you have to go with different oxide layer materials, where here you can scale down the size of the oxide layer, oxide material, right? So yeah. So this is just electric field in the different regions of the device structure. I have just calculated. I am sorry. We'll break for tea and then one paper discussion, article discussion we'll have. I will conclude in 1 minute. CNT FET results also you can see at different node technology 22 and 14. 14 with low dielectric material K value and high dielectric material, and at 22 nanometer what is the current curve. You can just see with voltage what is the current. So this is a curve at high K material. The current driving capacity of the device is high here. Ion the magnitude is more here. So that is far better compared to silicon based devices. So few simulation I have carried out on inverter and a few circuitries using FinFET that I have. If somebody is interested, we'll discuss. Otherwise, I'll wind up. So this is simple inverter I have built using FinFET, and delay, power, what is the power consumption in 14 nanometer and 22 nanometer, just comparative analysis I try to do. And finally, I have concluding that the power consumption in FinFET based circuitry will be less and the switching speed will be faster, and some memory designs also LT Spice I have used, and I have simulated using the same FinFET structure. So that is far better compared to silicon based devices. So static noise margin is an important parameter in memories. Okay, more the static noise margin value, better is the capacity of the memory to handle the noise. Okay, that is static noise margin. So I have achieved these values. 207 millivolts value for 22 nanometer, and 40 nanometer the value, static noise margin value is reducing, so the capability of handling noise will be less here as you scale down the device size. So like this, power, delay, everything are calculated. It is, these are the values. Okay, so since it is 3:30, people are waiting. Okay, we'll have a break for tea, and then I think we can go for directly article discussion. So anybody interested in FinFET or nano device level work, we can discuss definitely, because even with NC Patils and few of my friends in other college, we are trying to form a consortium to work on this nano electronics, nano technology, VLSI area. We are open for collaboration, so we can, because we have to go beyond our regular pattern of working. We have to go beyond our box. We have to think and do something which is it is a value addition to our system, own system, and it will be win-win situation for both the parties. So I think Anant sir and Patil sir all will agree definitely. In future we'll try to collaborate and try to discuss more on these technical aspects and try to draft a proposal collectively. At least we are thinking at least now, but after a few days, few months, we should be able to execute something, some proposal to DST or to MIT or SERB, wherever it is possible. Let us make an attempt and try to. Thank you for your patient listening. I will conclude. Thank you. Yeah.
Based on research going on right now, when do we expect to implement this technology?
Yeah. It's very difficult to say because it is at research level. See, when people will start purchasing the product from you, commercialization. Industry has to commercialize it. To commercialize it, so many things they have to see. It is not researchers will say this is the best device. Okay, so but when it goes to foundry, he says, oh, lot of difficulty in fabricating this because there are interfacing issues. There are foundry is not upgraded to fabricate this device on the chip based on this device. Lot of issues, lot of challenges. So they have to upgrade their fab labs itself, and that requires huge money to invest. So we cannot say that this product will come immediately after 2 years or 4 years. But definitely, see, as I said, FinFET based memory, they developed in 2016. They started working. Samsung is a company. I have gone through complete literature, and that's why I am commenting. 2002 they started their work, and 2016 they released the product in the market. I have proof, released their materials in the website, and they have only claimed that we took 14 years of effort. Just SRAM memory they built using FinFET. You see how much time it takes. So it is a future. There is plenty of scope for the improvement. So let us keep working towards that. Thank you.